Hello, my name is Jonah Wu, and this is my Physics 2211 Lab for Oscillations. The purpose of this experiment was to analyze the motion of a spring mass system in which the mass swings on an arc while oscillating on the spring. I compared the predicted motion with the observed motion using a computational model using GlowScript and analyzed the energy within the system. For this experiment, the two key assumptions were the assumption of an ideal spring with no mass and negligible air resistance. The first fundamental principle involved in this lab was Newton's second law, or the momentum principle, which states that the net force on an object is equal to the change in momentum over the change in time. From this equation, we can derive the velocity update formula and the position update formula as shown. The second fundamental principle involved in this experiment was the energy principle, which states that the change in energy of a system is equal to the work done on the system by the surroundings, plus the transfer of energy between the system and the surroundings due to a temperature difference. Consider what is in the system with scenarios involving energy and the transfer of energy. In particular, for this lab, I put everything into the system, with the spring, the mass, and the earth being in the system, and the surroundings having nothing. Therefore, the change in energy of the system is equal to 0, as nothing in the surroundings is performing work on the mass, and we can assume that the temperature difference is negligible. As previously stated, the system is the earth, the spring, and the mass, and the surroundings is nothing, and therefore the change in energy of the system is equal to the sum of the change of energies in kinetic energy, gravitational potential energy, and spring potential energy, which is equal to 0. The mass of the object, as stated in pre-lecture videos, was 0.402 kilograms with an initial velocity of 0 meters per second and initial position as shown. Here is the video of the tracker analysis of the spring mass system. Here is my GlowScript computational model. Pay attention to the initial conditions, the calculations of forces, velocities, and displacements, and the calculations of energies. As you can see, we initialize the ball with a mass of 0.402 kilograms with an initial position of velocity as shown. We also initialize the spring constant to 6.83 as from the pre-lecture videos, and also the relaxed length of the spring as 0.123 meters. Here you can see the calculation of the vector L, which describes both the length and orientation of the spring, and S, which is used in the calculation of spring potential energy. And here you can see the calculation of the initial kinetic, gravitational potential energy, and spring potential energy, with total energy being equal to 0 at all times. In this loop, you can see that we calculate the net force using the addition of the gravitational force and the spring force to calculate net force, and we use the velocity update formula and position update formula to update the ball's, the mass's position and velocity. And we also update the various energies as shown before. Here is a video of the tracker of the GlowScript model running. From the experiment, we generated these graphs, which are the change in energy versus time and the x position versus time and y position versus time. For the change in energy versus time graph, we can see that the change in total energy is always equal to 0 due to our definition of the system. The change in gravitational potential energy and change in spring potential energy are of similar magnitudes but of opposite signs and oscillate at the same rate. And the change in kinetic energy oscillates at the same rate but is much smaller in magnitude compared to the other energies. For the position versus time graphs, we can see that the x position versus time graph, that the model and the experiment are very similar. However, with the y position versus time graph, there are more inconsistencies between the model and the experiment, suggesting that the model is more accurate at modeling the x position versus time. These sources of error could be due to neglecting smaller forces acting on the mass, like air resistance, assuming a point mass system which excludes rotational kinetic energy, and inconsistent measuring of the center of mass in tracker. Is the energy principle satisfied? Yes, at every point in the change in energy versus time graph, the sum of the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy equals 0, as shown to the right. The oscillation periods, an average over 4 oscillations from what I calculated, by x position was 1.683 seconds, and by y position was by 1.52 seconds. And the difference is 0.163 seconds. What does this imply? It means that there might be unaccounted forces that we didn't account for in our calculations, like air resistance, inconsistent tracking in the center of mass, and this will affect our calculation of the spring constant and therefore how the mass moves.